Good morning friends. Today I like to discuss the basic electronics. The module, as we have discussed module 1, so we discuss today as module 2. Module 2 is concerned with the energy formation, that is energy band formation in the semiconductor materials. Basically, whenever we try to define the crystal or diatomic molecules, then there is a formation of energy curve on the basis of the interaction potential, and this is known as potential energy curve for the formation of molecules or crystals from the atomic states. For this, we consider the famous potential energy curve. The potential energy curve is a curve which is used to define the molecular state from the atomic state. This is atomic state and here is the formation, and then it is molecular state. So, from atomic state to molecular state, this energy curve used to explain. Suppose this is the point at this particular position, A is the molecule, this molecule is A, and here it is the molecule B, B molecule is kept at the origin. So, there are two atoms, these two atoms are separated at a certain distance, and when we bring closure, then we have to move one of the atom towards the other. In this case, what we want, B atom is fixed at origin and A atom is moving towards the atom B, that is origin. So, when two atoms are interacting, then by the law of physics, their energy, their force of interaction will increase, and this increase of the force expressed in the negative part of this potential, which is negative of U, that is attractive. This is attractive. So, this point, if you further bring this one is, so you will confine this one is, so the negative value of potential is increasing, it means there is a increase of the interaction. So, at this particular point, when you bring the atom, this atom A, this atom A, this is A double dash states. So, you find this one is the maximum value of U, this is U max. This U max gives the concept of interatomic distance. This is interatomic distance at the equilibrium state. At the equilibrium state, this is also known as the internuclear distance, because we always taking the distance from nucleus of A to nucleus of B. So, this particular value of R0 is termed as interatomic distance, interequilibrium distance, internuclear distance, and finally, this particular distance is also called as bond length. This is also known as bond length. So, from the atomic state to molecular state, when two atoms are combined, then they will remain at a certain distance place, and that certain distance place is known as bond length. This value of this bond length is approximately of the order of 2 angstrom in the normal case. It may vary, that is, you can say in some cases it 1.5 angstrom, in some cases it is 2.5 angstrom, and there etc. these value. So, the bond length is. Now, the interesting case is from this point, if again you are coming closer, if you are coming closer, A is closer to B, then what will happen? The nature of curve is in this way. So, uphill task of this curve represents the decrease in the negative value of energy, and this point is the point which is RC. RC is termed as closest approach distance, RC, means you cannot compress below this distance to A, this A triple dash, and here it is B, because whenever we comes to this point, then what will happen? The nucleus of B and nucleus of this is A, this is B nucleus, and here it is the electron clouds. So, the repulsive nature of force arises due to the close interaction of negatively charged electrons and positively charged nucleus. So, these are creating a repulsive force, and again you are coming closer to this point. So, there is a fast rise in the curve in the positive, that is fast rise produce repulsive force or repulsive, this is the positive energy. So, the potential energy curve, this potential energy curve is the curve which defines how two atomic states converted into the molecular state for the two. Now, in case of silica, the one silica form the other silica with bonds as so the valency of silica is 4, the outermost electron in silica is 4. So, these 4 electrons are co-bonded with neighboring 4 silica atom, and then they form the octet, and this will make a stable state. So, in this stable state, if we plot the energy levels, then what we find? This is the first orbit. This first orbit is something like this is nucleus. So, this is n is equal to 1, here it is n is equal to 2, and this is n is equal to 3. This is n is equal to 3 for Si. So, this Si is the first orbit is 2 electron, second is 8, and the third is 4th. So, these subcells, these are subcells. So, this is the S subcells, here it is a, in case of n is equal to 1, this is the S subcells, this one is n is equal to 2, there are 2 subcells, and for n is equal to 3, again there are 2 subcells, and this one is represented at 3s2 and 3p2. So, what we have? There are 2 electrons in 3s2, and there are 2 electrons in 3p2. Now, these 2 electrons are separated with some energy, but due to the hybridization, these 2 electrons from S subcell combined with 2 electrons of P subcells to form all 4 electrons of the same energy state. So, how this hybridization are taking in the case, this one is when you are bringing close, then what will find, there is a splitting of the energy states after finding, and this energy state is something like this, and here it is the energy state something like in this form. So, what we find, these two electrons and these two electrons combine to make these 4 electrons of the same energy state, and that is why the valency of the silica is 4, and this part is something like you have. So, these are the state, this is called as filled state, and this state is called as empty state. This is empty state, and above this one is above this one state, this one is again the state of conduction, this is a state of conduction. So, what we find in this structure, these lower state, these are already filled state, because the complete octet is there. Complete octet is there means you have something like this. This is the complete octet, this is the filled state. So, this one is a filled state, this one is the filled state, and the above of that is the filled state of the electron 4. So, we call it a valence band, this is the valence band. So, this one energy state n is equal to 3 is also considered in this case. So, what we find ki the energy up to this state is completely filled, and there is a space, and above there is a conducting state, means if the electrons comes to this place, then they will start off the conduction. So, how this energy curve is taken from the potential energy curve? The potential energy curve, as you see, there is a variation of this energy curve in this part. So, this variation is taking in this case also as the case is similar to the case of variation, something like this. So, these are the potential energy curve, and here it is also potential energy curve. So, from one silica to another silica and the other silica, these kind of the formation is there, and that is why there is a formation of energy band. So, what we find? We find this one is as in case of silica, we represent this one is the valence band, and here it is conduction band. This is conduction band, and this valence band is filled. This is the filled. Here it is empty state, and here it is gap. This is gap. So, if we express the terms of energy, then we call this the valence energy, where EV is valence energy state, and EC is conducting energy state. This is conducting energy state, and this valence energy state, here it is the valence energy state. This energy EV is valence energy state, and this is the conducting energy state. So, this EV, this EC corresponds to this EV and EC. So, what we are discussing here, we just have this kind of the energy level curve, and this energy level curve is just a way to express the combination of the silica atoms in the formation of crystal, in the formation of bands. Now, on the basis of the band gap, this band gap, that is delta E of G, is nothing but EC minus EV. Normally, this value is 1 electron volt, this value is 1 electron volt, but in case of silica, it is 1.2 electron volt at 0 Kelvin and 1.11 electron volt of silica at room temperature, that is 300 Kelvin. So, this one is the energy gap that is there in case of silica at room temperature. Now, the semiconductor can be classified in two broader categories on the basis of energy band, on the basis of the conductivity. So, the classification of semiconductor, this is classified in two part, that is on the basis of temperature, and here it is band shape. On the basis of temperature, we can classify as two group. One is known as intrinsic semiconductor, as it is semiconductor, and other is extrinsic semiconductor, means T is equal to 0 Kelvin, it is bad conductor, T is equal to 300 Kelvin, and doping, this one is conducting. At this intrinsic semiconductor, the charge carriers Ni square is equal to A, this T e raised to the power minus Eg upon Kt, where this Eg is, or you can say change of this is band gap, as we have discussed about the 1.11 electron volt or 1.2 electron volt in SI. The second one is doping. On the basis of doping, we have in short, this is P type and here it is N type. P type, N type semiconductor, that is trivalent and pentavalent. We will discuss detail later on. On the basis of band, there are again two type of the semiconductor. One is direct and other is indirect. Semiconductor. Direct semiconductor can be expressed like this. This is the valence band, here it is conduction band, and this electron is here. When it jumps from high energy state to lower energy state, that will generate the H nu photon, and this H nu photon is nothing but there is a concept of photoelectric effect or LED in the formation of LED. The other one is indirect. In case of indirect, you see this one is the band gap, that is valence band gap, and here it is conduction band gap CB. So, what in this process is, first it comes to here, that is called as phonon, and then there is a photon, So, phonon-photon interaction, that is phonon-photon interaction, and the example is very clear, as we have silica, germanium is the example of indirect semiconductor, and gallium arsenide, through which we have light emitting diode, is direct semiconductor. That is why this has the higher energy. So, jump of electron from high energy to low energy is this much. The energy of this K, this is E, and here it is, this one is a K vector. So, this is H K square upon 2 m plus some value of energy. So, this E k is related with this energy state. So, this k is propagation vector and this is energy at this case. So, on the basis of the temperature, we classify intrinsic or extrinsic. At high temperature the material is extrinsic, as well as by the doping. At 0 degree temperature it is intrinsic. Intrinsic means it is bad conductor, and the charge carrier is something like this one is. So, this one is the classification. Now, at this point of time, I would like to discuss the extrinsic semiconductor. I would like to discuss the extrinsic semiconductor. The extrinsic semiconductor the conductivity of the material, will increase by the doping, that is impurities in the semiconductor. There are two types. Semiconductor, as first is N type and second is P type. P type, extrinsic semiconductor, here it is extrinsic semiconductor. The P type and N type extrinsic semiconductor suppose there is N type and here it is P type. So, in case of N type, the impurity is pentavalent. pentavalent impurities, that is say nitrogen, phosphorus, antimony, bismuth. So, the most common use of this is phosphorus, that has 15 atomic, 2, 8 and 5 are the atomic configuration. So, if we consider this pentavalent, why it is called pentavalent? Because the outermost electrons are 5. Now, if we draw the structure, so phosphorus, suppose this is the phosphorus and this phosphorus has these 5 electrons. This phosphorus has these 5 electrons, and this phosphorus has to bond with the silica, this phosphorus bond with this silica, this phosphorus is bond with this silica, this phosphorus is bond with this silica. So, these 4 bonds contribute the concept of stability, of octet rule, and rest of the silica crystal is something like this. Something like this. This is the crystal structure of the N type semiconductor. Here it is complete octet is there in this form. So, what will happen? In this case, in this crystal structure, what we have in this case, this one is the excess electron. This one is the excess electron. This is the excess electron. Means at this point of time, phosphorus does not require this electron. It is behave like a free electron, because in the phosphorus, as we have expressed in this case, there are 15. So, these are 15 electrons, and inside the nucleus there are 15 protons and 15 neutrons, suppose. So, with these combination, the phosphorus is neutral. So, this phosphorus is neutral, and what we are doing? This phosphorus is doped. This phosphorus is doped in the silicon crystal, which is neutral. So, one neutral is doped with another neutral, then whatever the system will form, then that system will neutral. This neutral and this neutral makes a system neutral. Why I am emphasize this one? Because if one have to put the question is, what type of charge on N type semiconductor? What type of charge is N type of semiconductor? The answer about 90% students reply negative. 90% student reply negative, which is wrong. The correct answer is neutral. Why it is neutral? Because P is neutral, Si is neutral. So, the system is neutral. Where it is negative charge? This electron, just the excess electron, note the excess electron, the question is, what type of charge on N type semiconductor? Answer: 90% students say negative, and this negative is wrong, because the correct answer is neutral. Why it is neutral? Because phosphorus is neutral, silica is neutral. If both are neutral or combined to form any combination of structure is neutral. So, the excess electron, note, the excess electron is excess inside the crystal, but the corresponding charge, the corresponding positive charge is already in the nucleus of the phosphorus, and that is why it is neutral. So, this excess charge, if this electron move at this place, so what will happen? This electron is free, it moves somewhere else. Suppose there is a electron, so this electron is moving. So, in this way electrons start up moving from this way to this way to this way to this way. So, this one is a pathway of electron. This is second pathway of electron in the crystal, and in this way electrons start up moving freely inside the crystal, and the conductivity, and that is why the conductivity will increase in case of N type semiconductor. Now, in case of P, just for another 5 minutes, in case of P type semiconductor, P type semiconductor, they are of need of trivalent impurities, and these impurities are of aluminum, indium, etc. Suppose we are using this aluminum, means the valence electron, the number of valence electron is 3, number of valence electron is 3. So, if we take the structure of this aluminum, so aluminum has this electron as its site, and this aluminum electron form the crystal with silica atom, this silica atom, as this one is silica, this is the bond, this is the silica, this is the bond, this is the silica, this is the bond, this is silica, this silica. So, what is the speciality? Speciality is, in this case, the first electron, this is the first electron, this second electron, this is third electron. There are 3 electrons for the outermost orbit of aluminum. For the octet, we need 8 electron. For the octet, we need 8 electron. Here, the number of electrons after the sharing are 2 plus 2 plus 2 plus 1, that is 7. So, there is one lack of the electron. So, what will happen in this case? These electron, any one of the electrons, this electrons comes to the place. This place is empty place. This one is a empty place. This one is an empty place, and this place is occupied by 1 electrons from the neighboring silica, So, what will happen? This electron occupied in this place and there is a vacant place at this particular space, means there is a vacancy, here it is. And then what will happen if there is another silica here? So, this electron occupy this place and there is a vacancy at this place. So, what will happen? Basically, the electrons are moving, these are the pathway of electrons, this is the pathway of electron. This is the pathway of electron, but the empty place is moving from this place to this place to this place, means pathway of electron is something in this direction, the empty place moving in the opposite direction. So, pathway of empty place, and this empty place is termed as hole. This empty place is termed as hole. So, from this configuration, the characteristic of hole is number 1 again neutral and less mobility than electron, we will discuss later on in detail, and change in mass, that is MP is different than MS, and this is later on it is called as effective mass. So, in this way again the aluminum is neutral, this silica is neutral, and they will form a crystal, that is p type crystal. So, it is neutral. So, what we find again the p type is neutral. Now, if put the question, what type of charge on p type semiconductor? The most of the students say p type crystal is positive. Again the 90% student reply it is positive. Which is again wrong. That is not positive, it is neutral. So, the takeaway lesson is both N type semiconductor as well as p type semiconductor both are neutral. And then on the next time we will like to discuss about the energy level. 5 मिनट और चल सकता है? ओके, आप उसको एडजस्ट करिए. लेवल कर्व, if we draw the energy level curve, then the energy level curve of this p type and n type is something like this. This is a valence band, here it is conduction band. You take this one is the group of n type, this is n type, and here it is p type, n type, p type. So, what n type, there is excess of electron. So, excess of electron gives the concept of rise of the valence band. This one is rise of valence band, and the gap, this gap ED, donor energy, the ED donor energy is about say 34 million electron volt, and the phosphorus is termed as donor atom, and this mu of n is greater than mu of p as for the whole, and majority charge carrier is electron, minority charge carrier is hole, and the crystal diagram of this p-n type is, these are the electrons, majority charge carrier of the electrons, these are the electrons, and minority charge carrier are holes. So, this one is hole, less in number, and this one is electron. So, this similarly, we have this one is a hole in formation of hole inside the valence band in case of p type. Then the lowering of, this is lowering of conduction band, and this ED as earlier case, here it is EA. EA is the acceptor energy is equal to 16 million electron volt, and this is aluminum is acceptor atom, this is acceptor atom, and this mu of p is less than mu of n, mobility, and the majority charge carrier this is hole, and minority charge carrier are electron, and this crystal structure is something like this. These are the holes. Holes are majority charge carrier, these are holes, and here it is some electrons, and these electrons is minority charge carrier. So, this is about the p type semiconductor and n type semiconductor. The crystal is form of this p type and n type semiconductors are given in this form, and this is the concept. This one the concept of p type and n type semiconductor. This is for module 2. In the next module, that is module 3, we will discuss about the p-n junction, when we form one p type semiconductor to another n type. So, we will form p-n junction. Thank you.